Once again, welcome. Great to have you here today at Cisco. My name is Vega. I am Senior Product Manager in the engineering team that brought to you Cisco application-centric infrastructure and the Nexus 9000 platform of switches. In my role, I am responsible for open source initiatives out of the group. I am very passionate about complex distributed system problems and building products, not problems, around those and taking it to market and making it easier for our customers, taking bleeding edge technology from web scale, open source, and to consumable enterprise products. Today, over the next hour, we're going to talk about Kubernetes and ACI, as well as ACI multi-site. These are two of the major features that came out with the latest release of ACI, ACI 3.0. Before I take it off, anyone who has not heard of Kubernetes?
Heard of or understand?
How well do you understand Kubernetes?
I've heard of Kubernetes.
Okay.
I'm a storage guy, so I'm a little slow.
Okay. So let's talk a little bit about Kubernetes to start out. Kubernetes is based off the operating system that runs Google data centers. Google in the early 2000s had the problem that they wanted to complete a query for an entire terabyte of data in less than 10 seconds. So they had to figure out the most optimal placement of containers that would serve that query across their entire data center. As much as they love solving theoretical computer science problems, they got into the public cloud market, and they had to share the infrastructure resources they were dedicating for the internal engineering to share it outside. With that, they had to bin pack all those workloads to maximize the efficiency of all their compute resources and energy utilization across the world. They open sourced the system they had developed to manage all the network and the compute to do the most optimal placement of containers, basically managing containers at very large scale, and the order of thousands and millions of containers at any given point in time. Kubernetes is great many things. The open source community loves it, developers loves it. It's great for scheduling and managing the life cycle of containers, but Kubernetes is very hard to bootstrap. If you want to get the experience of running Kubernetes in the public cloud into your private data center, there is a lot of work involved in setting up the required infrastructure to do so. The networking requirements for Kubernetes to work are quite complex, and people have gone down the path of doing so, have walked the path of untold misery. With ACI, we want to simplify it and make sure you obtain the same experience of running Kubernetes in the public cloud that you can do so in the private data center. Another set of challenges exist. Containers are great, but no data center environment is legacy-free in reality. There are physical databases, new systems that may be brought up will still have dependencies to those legacy databases to interconnect to the data that's already stored and available there. Interconnecting containers to those physical databases or anything in virtual machines, it's hard. There's different set of tools for it. No matter how much level of automation you come up, it's still quite a cumbersome task to interconnect containers to anything else. It's not really simple. Making sure that not just the connectivity requirements, but the security policy is consistent across the different layers of the stack is also a challenge. And another problem inherent to most deployment platforms as Kubernetes is they were a homebrew in environments that didn't really have a requirement for governance or isolation. They came up in development teams that didn't have any level of compliance and didn't have auditors coming in or didn't have to abide by a security policy. So they were never developed around concepts of multi-tenancy for isolation of different organizational groups or different clients consuming it. Naturally, as Google got into the public cloud environment, they built in multi-tenancy constructs around Google Cloud, but this never made it part into what they open sourced as Kubernetes. So how do we fill those gaps in integrating Kubernetes on top of ACI? If you're bringing Kubernetes into your private data center and we are proposing, well, the best infrastructure to do so is ACI, why is that? ACI, when we developed it, we were looking at a number of issues to address. One of them was virtual machine mobility. Things move around in the data center. We wanted to make sure no matter where a workload would come up, we couldn't deterministically predict where it would. But at the time that it did, that we would instantiate the connectivity requirements in the security policy right there at that point in time. And we do that very well. We knew containers were coming, and it was a harder problem. Why? Because containers have a much larger rate of fluctuation and refactoring than virtual machines. They may take a fraction of seconds to come up. They may run for a number of seconds. If someone runs a container to do 4 pings, and we have to wait for the first packet to figure out what workload is that, where did it come up, it's already too late. If we did that, if we ate that first packet, we just compromised 25% of the availability of that application. So we had to come up with something faster for containers, and we did. By reusing the network automation and APIs that we built, we know even before a container is going to come up, the moment the scheduler, the control loop that says a container is to be initialized in this particular server that's part of your Kubernetes cluster, ACI is notified. We do the plumbing both in the infrastructure and at the virtual switch level. We create all the connectivity requirements. We do the IP address allocation. And we know even before it's ready to start talking where it is, what were the requirements, we plump those across. It becomes very easy, and we knew it was coming. In ACI, every single network endpoint is an object. We built this system from the ground up, API-based. Everything is entirely modeled in a directed graph. To us, we do not differentiate the form factor of a network endpoint. It's all endpoints. It's an endpoint object. For us, it's very easy to interconnect a container object to a database that's physical or to a virtual machine. It's very easy to build out that application profile that we call it, design it in a declarative fashion. An application architect may say, this is my app, maybe a 3-tier app, regardless of its containers or it's not, just say this needs to connect to that cannot connect to this, and we built it out. We simplify the routing and switching of interconnecting containers to everything else. Now, container environments have a very heavy reliance on load balancers. Why is that? If you're accessing a web server from Amazon, you do not care whether there's 1,000 containers that are serving that web request for that particular service. You care about a virtual IP. But as Amazon scales up or scales down those 1,000 containers to any other number, that is transparent. But in the container world, if that's containerized, the IP address allocation is not deterministic. Containers are ephemeral, they come and go, they get different IP addresses in a pool. I believe most of you in the audience have infrastructure backgrounds. That problem of how do I configure the load balancer if I don't know what IP addresses are going to be behind the VIP, how do I do that? So that needs to be entirely automated, be transparent to the user, and again, through having built a proxy and a broker between a Kubernetes and ACI, we know as containers come and go what addresses get created, and we automatically programmed the fabric. We use our embedded capabilities for load balancing. We do load balancing in hardware. Whenever north-south a packet comes from outside into a service, we use what's called policy-based redirect. We do that in hardware, utilizing equal cost multipathing, and we use the cross-sectional bandwidth that it's inherent in a spine leaf architecture in a data center fabric. Now, as for security, this is particularly hard. You have development environments where what they know is, well, I expect everything to connect to everyone in my team, and anything that I brought up, I shouldn't have to open up network ticket. Now, as things move on to production, that becomes a challenge, because how do you map an environment that was Wild West into something that is tightly controlled? Engineers know a shadow IT model, but infrastructure, InfoSec, and network know something else. So how do we retain what developers get in the public cloud while bringing back governance and control to the infrastructure team in-house? We built a model where we honor the Kubernetes Network Policy API, that is the Kubernetes security specification, for within the cluster. Now, if you want the enterprise model, we present this bi-model approach where you can build ACI contracts and ACI policy around the entire cluster or around the different levels, the hierarchical object level within Kubernetes of the cluster. From a cluster, you go down, you have a namespace, which is an organizational construct, basically a tag for different groups to assign resources to different teams. You can apply that at a deployment, which is a set of replicated containers, or you can do it down to a very low-level container object. So if you want to restrict of this container, I'm going to make sure that we program and enforce rules both in the virtual switch on the Linux server where that runs, or on the switch, if it has to traverse the wire, make sure we restrict and we enforce that doing ACLs and contracts the way we do in ACI. Monitoring. Monitoring, it's challenging. There are tools that exist, again, for the different layers of the stack. You may have a monitoring tool for Kubernetes. ACI has its own set of monitoring capabilities, and everything else in between. But how do you correlate? How do you map what in the Kubernetes world means what in the infrastructure? This often turns out in a lot of time spent in war rooms chasing down the whole what is what, where is it, attempting to resolve incidents. We, by exposing every container as an object and everything else within the Kubernetes cluster in ACI, be it a namespace, be it a deployment, be it a container, the cluster nodes itself, we represent the object and all its metadata. We visualize, you get the stats, you get the logs, and in addition to it, we provide you with the correlation of what in the container world maps to what in the physical world. So what container and what host, what virtual port, the far end of that virtual port, what is the physical interface on the switch. If you want to see one service talking to another service for east-west, we show you where those services reside and where is the traffic that traverses the fabric, what actual ports is it going through, ultimately reducing the mean time to troubleshoot to resolve an issue. I had spoken about multitenancy. ACI is multi-tenant, and by its multi-tenant facilities and provisions, we map every single Kubernetes cluster deployment to an ACI tenant, ensuring hardware-level isolation between resources allocated for one cluster to the other. Questions so far? Great. So let's take a deeper look into how it all works. What does it mean? So you have your ACI fabric. You have Kubernetes running on top. This is your Kubernetes has a master that makes all the scheduling decisions of where containers are going to run. And it manages servers by order of control loops. It's as declarative as ACI is. If I launch an application in Kubernetes and say this application has this set of deployments, each deployment has this number of containers, For itself, Kubernetes says, well, if I'm running service web, it has to run 3 containers at any given point in time exposed on this port. It will query the nodes that are part of the cluster. How many containers are you running? The server will say, I'm running 0. Well, you're supposed to be running 1. And at that point, it starts. That way, it is able to self-heal if it's out of compliance with the spec, with the manifesto for that application. If the server goes down, if the container dies, it will discover that through the feedback mechanisms and relaunch it. We have the fabric in between, and Kubernetes has a network policy specification that allows you to isolate within the cluster, turn it on, and say, nothing is able to talk to each other unless specified in this YAML file. Just as a format, Kubernetes uses YAML for all this file descriptors. We take that network policy, and that policy within Kubernetes is just a specification. It's not an enforcement. It doesn't guarantee. It doesn't ensure that things are not going to talk to each other. You need an enforcement mechanism, be it IP tables, be it Open Virtual Switch. In ACI, we ingest that network policy, we render it, and we push it to the Linux server, and we do the enforcement by means of Opflex. That's our protocol for policy exchange. And we do the implementation itself in OpenFlow rules and Open Virtual Switch. Now, go ahead.
Around control plane,
Yes.
that workflow. Is it that I create the workflow, the policy, the intent that I want in ACI, that policy is then pushed to Kubernetes to create the profile and then, again, enforced by ACI directly? So do I have to actually ever see a YAML file in order to create a policy that ACI will enforce?
You do not. If you're the ACI administrator, you go about your job the same way you do today. You create policy directly in ACI. It will be pushed, and it will enforce those hosts. Now, the DevOps team that doesn't care about ACI and should not need to be bothered with learning ACI, they write their YAML file the same way they would do in Google Cloud or in AWS. They are migrating the application in-house. They put in the exact same file, and we will do the enforcement without them needing to care how it's done. They just have the assurance, the guarantee that it is applied. So ACI is ingesting both from the APIC API and from the Kubernetes.
So from
spec.
visually, I can go back to Kubernetes, ingest those YAML from my interface, ingest those YAML policies into ACI, and visually it can be represented from ACI administrator perspective as an ACI intent-driven policy.
Correct.
Okay.
So we call what we ingest and render from Kubernetes an APIC host protection profile. That is what's pushed to the server. We visualize this as an object in ACI, and we give you the stats, and the ACI administrator can interpret it without having to translate verbally with the DevOps person, what does this mean? They see it in their own language.
Okay, I get this.
Yes.
How would I implement this if I didn't have ACI? Because clearly the point is how much easier this is, but I don't know what hard is yet.
Would need to,
if I was still running 6509s, how would I make that work with Kubernetes?
There are open source projects that exist that do implementations in IP tables. So they take the network policy API, translate it in IP tables.
So
one of those is Calico, that
Okay.
company you might have heard of.
So Calico will take the YAML and translate it into an IP tables spec?
Correct. There are other open source alternatives to it, or you can build your own, which is quite a cumbersome task.
We're not building our own. We're smarter than that.
No. Which is like the network automation and APIs have been built. We want to make the job easier. People shouldn't, from infrastructure, they shouldn't become developers to use this. The machine should figure it out, which is what we're doing here. We are giving you time back to make more strategic decisions and spend less time tinkering with it. With that in mind, by retaining the experience, we needed to make sure that the exact same YAML file to create the application in any public cloud provider, you could take it without modifying it, spit it onto Kubernetes running on top of ACI without making any changes and ensuring it would work. If you run in AWS or you run in Google Cloud, you acquire the load balancing services that they provide. You pay an extra for that. In-house, you need to either come up with HA proxy or put in whatever load balancing you have in place and figure out how you're going to automate it. It's quite a cumbersome task. In ACI, we made it completely transparent. The moment you, and we're going to see it into the demo, it's going to be well illustrated, be clear at that point. The moment you create a set of replicated containers, ACI takes that and that are exposed externally to be accessible from the internet. We create the policy-based redirect. We create the load balancing provision. And also, well, microservices are not only load balanced north-south, they're also east-west. In application tiers, they have to communicate inter-service one to the other. We do buy our own extensions to Open Virtual Switch. Open Virtual Switch load balancing for east-west. It's layer 4 load balancing. And for those familiar with ACI, you may be familiar with the concept of virtual machine manager domains, how we do integrations with vCenter, how we do integrations with Azure, how do we do integrations with OpenStack. We have extended that to include Kubernetes, so you can visualize from the APIC GUI the entire Kubernetes cluster, all its objects, all its statistics for each of the different objects, namespaces, deployments, services, and pods, and the correlation of those objects to the physical components of the system. Now, let's take a look and back to your question. Where is the separation of responsibilities drawn? What is the delegation of tasks? We would have two personas that make use of the system. On the far right, you have the network administrator. The network administrator remains very much in charge of racking up the system, bringing it up, making sure there's a converged data center fabric. At that point, they define what set of network resources are to be carved out to present to the Kubernetes cluster. What VRF, what external interface to connect to the internet, what set of VLANs. Optionally, they can create endpoint groups and contracts for anything from and to the cluster to abide with the set of security requirements. And from a day-to-day perspective, they'll go about monitoring and observing telemetry the way they do today in ACI. They have all the troubleshooting capabilities. They can apply those to Kubernetes. Now, the DevOps team on the left, they install Kubernetes and they apply the ACI plugin by use of a single one-line bash script that will apply. It's called the CNI plugin, Container Network Interface, one of the proposed standards for container networking. We took the work that we've done in OpenStack for ML2, and we ported that over to CNI. They make the installation the moment they have a freshly installed system. They are ready to build network policy API. If so they desire, they build the definitions and the network policy. And they are ready to deploy and scale containers. Optionally, if they want to isolate their deployments, they can build EPGs and contracts from Kubernetes and push them into the system. Additionally, they are able to annotate. In Kubernetes, there's the concept of an annotation. Think of it as a tag or a label to be applied to objects to say, this will be placed in this specific EPG. So think of, I built an application, I run it in my development environment. I'm going to migrate this application to production. In its runtime, I can apply the tag And by applying this tag matching an EPG name, that will be automatically mapped to a corresponding EPG in ACI that would have predefined policy. So the migrating from dev to prod is pretty straightforward.
So
I can also apply the tags to.
We can get lost in the taxonomy a little bit. Can you reinforce EPG, the concept of an EPG? What does the acronym stand for again?
Endpoint group.
Endpoint group. And then from a governance perspective, so there's going to be people that run in two different modes. There's going to be the DevOps team that manages security, in theory.
Correct.
And then there's going to be the API team, the ACI team that manages security, or some other group. And taxonomies and contracts can conflict. So what the language that DevOps talks and the language that the traditional networking teams talk can be different. So there will be instances where we need to troubleshoot in between the two teams. So can you talk about when that contract is broken, when DevOps tries to do something that from a security perspective that ACI doesn't allow,
yes,
or the ACI team tries to do something that the DevOps team doesn't allow, how does that conversation?
Yeah, totally. That takes us to the next slide. So
can I ask before you go on? I just want to be, before we go on, my question lies right before Keith's question. On the network admin side, we create the Kubernetes system resources in ACI. That's defined in the network policy, right? You said VLANs and VRFs and that type of stuff. So then on the container team side, in the second step, they're building service definitions and defining network policy. What's the difference?
Network policy in Kubernetes is irrespective of what exists on the underlying infrastructure. Okay. Network policy in Kubernetes is this, and I can show you a YAML file for it, how the spec is written in Kubernetes, but take the example of a 3-tier app, web app, and DV.
Yep.
Within Kubernetes saying, web is going to be open in port 80, database is going to be open in 6379.
Okay.
That does not concern what physical interface, what is being trunked. It does not care about VLANs. Okay. It's very high-level application communication.
Yeah.
And ACI, the system resources are what interfaces, what switches, what VLANs I'm going to present to the Kubernetes cluster.
Yeah.
But at the moment you've handed that, they are in a sandbox.
Yeah.
They don't care about what's being used as long as things connect.
It's layer 2 stuff versus layer 4 and up.
Correct.
Okay.
That is very much the boundary.
Okay.
Keith, to your question, DevOps teams are not necessarily concerned about security.
Yes, that's true.
So we like say you're a developer, you work in an engineering team, you want to get work done.
Right.
You consult your peer. Oh, I just built this other service. Oh, that sounds perfect. I'm going to bring it onto my application. I don't need to write that myself. Just give me the service name. I will put up in service discovery, and we will interconnect. You don't care about the network semantics.
Right.
InfoSec and infrastructure are concerned. So within your world, within the Kubernetes cluster, by default, everything that you launch in ACI, we're putting it into a default EPG. And we're going to get to this, and I want to transition with that in mind.
So with that, the use case that I'm thinking of, and I like that you set that up, is that what happens when I create a service that is in conflict with my security policy. So I'm thinking, I'll create, as a DevOps guy, I'll create a helpful service that that basically creates a proxy. Right. That breaks the security policy. Like, no, proxies don't happen at the application level. It happens at the network layer.
Right.
So
here is the beauty of it. By default, anything you create in Kubernetes running on top of ACI will be placed into a catch-all default EPG. Endpoint group, once again, stands for, EPG stands for endpoint group. In ACI, what does that mean is a set of applications, a set of network endpoints that share the same set of connectivity requirements. And they can talk to each other without having to go through policy. We provide out-of-the-box cluster isolation. Everything within a cluster can talk to each other. There is no need for policy internally. Now, if they want to talk to the outside, they have to go through ACI policy. If they want to talk to any other business organization, any other business function, if they want to talk to the internet, policy needs to exist that allows for that. Now, to the point in your question, if you create a proxy at this level, you're only proxying internally. You cannot proxy to the outside because on the outside boundary, the network administrator is holding you and saying, no, you cannot go through this. I'm giving you a free-for-all in your deployment platform, but you're not going over me and doing so. Now, this is not entirely prescriptive. All the models are flexible and may be a combination with each other, but you can take subsets of a cluster that are called namespaces and say, for each team in engineering, for each of their namespaces, I'm going to map each namespace to a separate EPG. And contracts will control inter-EPG traffic.
So there's nothing to stop because it's logically, this is just this has to happen at the DevOps level, so from a policy perspective. But
correct.
If networking, if EPGs are transient, meaning that I have one EPG, two different sets of services on EPGs, a DevOps team creates a connection between EPGs. From an ACI perspective, it's allowed, but from a data security perspective, that translation may not, the work that they're performing inside, ACI doesn't have insight into that. That has to be handled at a different level.
So policy is never in conflict. It's always synchronized and consistent. I want to describe this last one to illustrate how, and just look at the key at the top right-hand corner. The black rectangle is ACI policy. The yellow rectangle is DevOps within Kubernetes. And one is always encompassed within the other. I want to get to deployment isolation. If we're launching things into prod, I want to make sure that every single tier of the application, everything that is described as a service in Kubernetes, maps to its own endpoint group, and that contracts tightly control that communication. Now, what you describe is if in my cluster, we have this free-for-all, let's role play again, you're the developer, but you want to isolate your app from all your peers. You want no one to access what you're developing. So you turn network isolation on within the network policy API, and that will restrict, you're going to say, no one can access but on port 80. That is the DevOps specification, and that is implemented internally to the EPG and enforced on the Linux server. The contract, the black rectangle, is what gets applied on ACI. In the interest of time, let me pick up the speed and show a quick demo. I am going to launch on a freshly installed system a 2-tier guestbook app. It has a web front end, and it has a Redis backend, 1 container for Redis master, 2 containers for Redis slave, and the front end is 3 containers. I'm going to launch that application into a single EPG, into the default catch-all EPG. You're going to see I just do the deployment. It gets placed in its own EPG. Then we're going to apply labels to the different tiers to move them to corresponding EPGs. We're going to showcase how the load balancing happens, and we're going to take a quick look at the VMM portion. Dismiss all down here. I have my freshly installed Fabric. By the way, the installer script would have created the tenant for the cluster and would have set up the VMM for me. I'm going to go to the terminal where I'm logged into a Kubernetes master. Is that large enough for everyone to see? So standard Kubernetes syntax. I want to show you what is running in the system at the time of having been installed. Standard Kubernetes components that would be part of any Kubernetes system. You have the Kubernetes database, which is etcd. You have an API server that brokers entirely all communication in the system. You have a controller manager, a DNS for service discovery, as containers come up to know where services reside. a proxy for every single node in the system. In this cluster, I have 3 nodes, 3 hosts, and the scheduler that does placement decisions. Abstractions exist as services, which are, again, set of replicated containers for the DNS and for the Kubernetes master. So here I am going to create the guestbook app. Let me show you how that YAML file looks like. So I have a file where I say I need service Redis master exposed on port 6379 to be 1 replica. I need Redis slave also exposed on port 6379 to have 2 replicas. And I need service front end exposed on port 80 to have 3 replicas. I can call out that file by doing kubectl and the namespace demo, create the following file, the file I just showed you. Hit enter, and it tells me the following services and deployments have been created. I can verify that by doing kubectl and the namespace demo, give me all the running containers. We see for 12 seconds, 3 front-end containers have been running. Redis master, 1, 2 Redis slaves. If we look at the service abstractions, service front end with that cluster IP address is going to communicate to the Redis slave on that other cluster IP address, which in turn is going to communicate to Redis master's cluster IP address. The front end has also been given an external IP address, which I have port forwarded on a router connected directly into the ACI fabric. I should be able to go to the IP address I have port forwarded as containers come up. I'll show you on the EPG where the containers have been placed by default. Kube default. We look at the operational tab. We see those 6 running containers with their network identity, what MAC address, what IP, what server are they running on, what's the reporting controller, what are the interfaces, both physical and virtual, and what encapsulation are they, is it VXLAN or is it VLAN, and what are those IDs. So I have my guestbook app, welcome to Tech Field Day 15. Let's see if we can write that. I can access my app, and I can write from the front end to the back end. That's all great. They can communicate to each other. What if I want to move those into production? What if I want to apply labels to those services for those to be placed in corresponding EPGs? Using standard Kubernetes format for annotations, I can do a kubectl annotate deployment. I'm going to annotate Redis master. You see the label on the bottom of the screen says key value pair name demo guestbook backend. Hit enter, tells me it's annotated. I want to do the exact same for master, and I want to do the exact same for front end. There we go. Front end, annotated. I would expect for this containers to H out from this screen. And you can see that happening. And the separate EPG, separate application profile, the separate EPGs, you see guestbook front end, the 3 containers have moved. And guestbook backend, the 3 database containers, if I must have a typo here, annotate deployment, Redis master, policy space, kube01, demo. Yeah, I have backend instead of backend. If I refresh here, I can see the containers start popping up. Kube01, demo, backend. I want to do the same for slave. Redis master, backend slave, annotated, refresh here. Those 3 containers move automatically. If I refresh my application, it continues to work. I can keep on writing to it. This, for it to work after I moved it to corresponding EPGs, I have contracts that were defined by either InfoSec or the network team that exist in here. If I go in and remove the contract that allows for Redis communication in ports 6379, delete that from ACI, I would expect the application to break. Front end, as you can see, no longer can read from the database. If I try to write to it, it's broken. It's very easy to quarantine from, and you see the control the network infrastructure suddenly gains. If I re-add the contract for Redis and I refresh the page, connectivity is restored. Every time that I refresh the application, the policy-based redirect for wherever any node that has a running container will be reported into an automatically created service graph with the IP addresses for each of the nodes. And if you look at the service graphs, I'm wrapping up in 2 minutes. I know I'm a little bit over time. If you look at the deployed graph instance, you will see in here, we automatically created for front end this insertion to load balancer. We're doing this in Fabric. If I go into Kubernetes and say, well, I'm running 3 containers for front end. In reality, I just need 1. And I scale the application down. You would expect to see the load balancer here on screen to go down to the single node instance that's now running a container for that. If we go back into the EPG and we scale up the application and say, well, you know what? 1 is too little. I need 50 containers for front end. You can see if I refresh here, as containers are scheduled and initialized, and you can see we're doing the IP address assignment. Even before the container is ready to start communicating on the network, we have already discovered. So we provide guarantee that by the time it starts, both the network connectivity requirements across the entire system and the security policy has already been created, even before the container is running. Yes?
Is there any monitoring with this to know whether or not you have enough replicas available and whether it needs to scale up? Maybe you do that automatically.
That is done within Kubernetes. So you define the specs for your application, what are the SLAs, and Kubernetes will make sure that is met at all time. The monitoring we presented in ACI, we look at the replica sets. And for front end, my VPN just dropped there. Flaky over here. But if I look at the service front end or the deployment front end, we will see the number. We will visualize the number of replicas. If I do the get pods here, once again, we see all the running containers. And here, the page refresh in the back end, we see all the replicas for that. And if the number of replicas is not being met, and whatever across any number of hosts you have in the system, Kubernetes will ensure, and you will have what's known in the container world C groups, like in vCenter would be the equivalent to the DRS of making sure those requirements are met and doing rescheduling for high availability and where can things be bin packed.
Okay.
And it's just, I think, my lack of experience with the Kubernetes stuff. The EPGs and policies you've created in ACI, but when you were giving us the overview of what each side would do, there was an optional create EPGs and policies on the container side of things. So they can't actually just randomly create containers and policies, can they?
So they can, it can be restricted and constrained for them not to. You don't want the developer to.
Okay, can we define the pronoun they in this conversation?
The container side.
The DevOps.
The DevOps team, right? Because
Yeah, they define it as
the network team would be building your EPGs and your policies, right? What you can and can't do on the network, who can talk, that kind of stuff, or the security team. But if you're on the DevOps team and you're the one that's deploying the Kubernetes and scaling it and all of that stuff, you can't just say, oh, and by the way, I'm going to create a new EPGs and new policies that let me do whatever I want on the network.
Because they would basically just be overriding, and
Right.
they end up creating 1,000 EPGs that mean nothing and
Right.
consume a lot of system resources. So we want to provide control to and rights to the top-level Kubernetes administrator. So when the system is launched, if you look at the Kubernetes application profile I'm pointing to on the screen, the EPGs you see there, the kube default, the kube nodes, the kube system, everything that's required by the Kubernetes infrastructure has been created from Kubernetes. So we evaluated whether we want them to be able to push EPGs, but we want to restrict that to the top-level administrator. Okay. Everything you see in the demo AP, those guestbook-backend, guestbook-frontend, those were predefined. If a label, an annotation applied to a container does not match either one of those two, it will be placed in the default.
Okay,
and
predefined by who?
Predefined by ACI, predefined by the network administrator.
Okay, that's what I thought.
Right.
So in Kubernetes, I can build a YAML file that selects an existing policy.
Exactly.